For nearly 40 years, everything humanity thought it understood about the planet, Uranus rested on 5 days of data. Not 5 years, not 5 months, 5 days, collected by a single spacecraft during a single flyby in January of 1986, and never repeated since. Every textbook description of Uranus's magnetic field, every model of its strange radiation belts, every assumption about whether its moons could support liquid water beneath their icy surfaces, all of it traced back to that one narrow window. In November of 2024, a team of scientists went back and looked at that decades-old data more carefully than anyone had before, and what they found suggests that the picture built from it may have been wrong from the start. Not because the original scientists made a mistake, but because the spacecraft that gathered the data happened to arrive at the worst possible moment, catching the planet in a condition that occurs less than 5% of the time. This is the story of the only spacecraft that ever got close enough to find that out, a spacecraft that did something its more famous twin never could, and a discovery that is now forcing planetary scientists to reconsider 4 decades of settled assumptions about an entire planet. It is also a story about how much of what we call scientific fact, for the outer solar system especially, is really scientific best guess, built on whatever brief window of data happened to be available, and quietly waiting for someone to check whether that window was ever a fair one. To understand why this matters, you have to go back to the summer of 1977, when NASA launched 2 nearly identical spacecraft within 16 days of each other. Voyager 2 lifted off first on August 20th. Voyager 1 followed on September 5th, and despite launching second, it was placed on a faster trajectory designed to reach Jupiter and Saturn first. At Saturn, mission planners made a deliberate choice that would define the rest of both spacecraft's careers. Voyager 1 was sent on a close pass by Saturn's largest moon, Titan, a target considered scientifically important enough to justify sacrificing everything that came after it. Titan was, at the time, the only moon in the solar system known to have a substantial atmosphere, and mission scientists were desperate to find out what it was made of and whether it might resemble the early chemistry of Earth. The gravity of that encounter flung Voyager 1 up and out of the plane in which the planets orbit the Sun, sending it on a permanent trajectory toward interstellar space, but ruling out any future encounter with Uranus, Neptune, or anything else in that plane ever again. It was a trade NASA made deliberately and openly, weighing one extraordinary target against 2 others, and there was never any guarantee that Voyager 2 would even survive long enough, or stay healthy enough, to reach either of the planets that Voyager 1 was giving up. Voyager 1 would go on to become the first spacecraft to leave the solar system, but it would never see another planet. Voyager 2 took a different path, one made possible by an alignment of the outer planets, so rare it only happens roughly once every 175 years. Because Jupiter, Saturn, Uranus, and Neptune happened to be positioned correctly during this exact window, engineers realized a single spacecraft could use the gravity of each planet to slingshot itself onward to the next. Saving years of travel time and an amount of fuel, no spacecraft of that era could have carried on its own. Voyager 2 took full advantage of it. It passed Jupiter in 1979, Saturn in 1981, and then, because it had not been sent on the same Titan-focused path as its twin, it continued on toward Uranus, arriving in January of 1986, followed by Neptune in August of 1989. To this day, Voyager 2 remains the only spacecraft in history to have visited all 4 of the outer giant planets, a record no mission currently funded or planned is on track to break anytime soon. Voyager 1 could not have made that trip even if NASA had wanted it to. The Titan flyby permanently closed that door the moment it happened. The Uranus encounter itself lasted only a matter of days. Voyager 2's closest approach came on January 24, 1986, and the entire useful window for close-range measurement was over in less than a week. What it found immediately struck scientists as strange. Every other planet with a magnetic field that had been measured up to that point, Earth, Jupiter, Saturn, had a magnetic axis that was at least roughly aligned with its rotational axis, the way Earth's north magnetic pole sits reasonably close to its geographic north pole. Uranus's magnetic field was tilted about 59 degrees away from its rotational axis, and it was not even centered on the planet, offset from Uranus's core by roughly a third of the planet's radius. On top of that lopsided geometry, Voyager 2's instruments detected intense energetic radiation belts trapped around the planet, alongside a magnetosphere that appeared almost completely empty of plasma, the charged particle soup that fills the magnetic environments of every other giant planet in the solar system. Scientists were left with a planet whose magnetic field looked like nothing else they had ever measured, and because no other mission ever returned to check, that single brief snapshot became the permanent scientific record. For nearly 4 decades, Uranus was described in textbooks and research papers as having the most extreme, most anomalous magnetosphere in the solar system. That description sat mostly unchallenged until a team led by planetary scientist Jamie Jasinski at NASA's Jet Propulsion Laboratory decided to revisit the original Voyager 2 dataset with fresh eyes. Publishing their findings in the journal Nature Astronomy in November of 2024, the team went back and reconstructed the conditions of the solar wind, the constant stream of charged particles flowing outward from the sun in the days leading up to Voyager 2's arrival at Uranus. What they found was that just before the spacecraft's closest approach, the dynamic pressure of the solar wind striking Uranus had spiked by a factor of roughly 20, an unusually intense compression event. That surge in pressure, the team calculated, would have squeezed Uranus's magnetosphere down to somewhere around 20% of its normal volume, a compressed, distorted state that, based on how often comparable solar wind conditions occur, is present less than 5% of the time. In plain terms, Voyager 2 did not arrive at Uranus during a typical moment. It arrived during one of the most unusual few days in any given multi-year stretch, and everything it measured during that narrow window was shaped by conditions that were not representative of how the planet normally behaves at all. The implications of that finding are larger than they might first sound. If the compression event Jasinski's team identified explains the empty, plasma-depleted magnetosphere Voyager 2 recorded, then the actual ordinary environment around Uranus may be far less exotic and far more similar to the magnetic environments of Jupiter and Saturn than anyone has assumed for the past 40 years. The tilted off-center magnetic field itself is likely still real and not an artifact of the solar wind event, since a planet's internal magnetic field geometry does not change over the course of a few days. But the intensely energetic radiation belts and the near total absence of plasma, the features that made Uranus's magnetosphere seem uniquely bizarre compared to every other planet, may have been a temporary condition rather than the planet's baseline state. Researchers involved in the study have said plainly that if Voyager 2 had arrived even a few days earlier, before that solar wind compression hit, it likely would have measured a magnetosphere that looked much closer to what scientists see around Jupiter or Saturn, fundamentally changing the story that has been told about this planet ever since. There is a second thread to this discovery that reaches even further than magnetic field geometry. Uranus has 5 major moons, and for decades, the near-total absence of water ions detected in the space around them was treated as evidence that those moons were geologically dead, unlikely to have any ongoing activity that might expel water vapor or plasma into their surrounding environment. That absence factored directly into how planetary scientists ranked the likelihood that any of Uranus's moons might harbor subsurface oceans, similar to what has been found at Europa or Enceladus elsewhere in the solar system. But if the compressed magnetosphere Voyager 2 measured had been actively driving plasma and water ions out of the system at the moment of the flyby, then the absence of those ions may say nothing about whether the moons are geologically active at all. It may simply reflect the fact that any plasma that had been present got swept away by the same solar wind event that distorted the magnetic field in the days immediately before Voyager 2's instruments were in position to detect it. An absence of evidence, in other words, may have been mistaken for evidence of absence for nearly 40 years because of a 5-day coincidence of timing. Distinction that matters enormously to anyone trying to prioritize where in the solar system to look next for the conditions life might require. Uranus was not the only one-of-a-kind stop on that itinerary. 3 years later, in August of 1989, Voyager 2 became the only spacecraft ever to fly past Neptune, discovering the Great Dark Spot, a storm system roughly the size of Earth, winds. Clocked at over 1,000 miles an hour, the fastest ever measured on any planet in the solar system, and finding that Neptune's largest moon, Triton, was geologically active, with active geysers, erupting nitrogen gas and dark material several miles into its thin atmosphere through its icy surface, a discovery nobody had predicted for a moon that far from the sun, orbiting backward. Relative to Neptune's own rotation in a way that still shapes how scientists think it was likely captured rather than formed in place. Like the Uranus data, the Neptune dataset has never been supplemented by a second visit. Every question scientists have about that system, every follow-up hypothesis, still traces back to the same few days of measurements gathered during a single pass in 1989. The pattern is the same one now driving the reanalysis of the Uranus data, a single flyby, decades ago, but treated for lack of any alternative as the definitive picture of an entire planetary system. The Uranus reanalysis, though, has produced consequences that reach directly into questions people care about today. If the compressed magnetosphere Voyager 2 measured had been actively driving plasma and water ions out of the system at the moment of the flyby, that changes how scientists weigh the odds for Uranus's 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon, several of which show surface features that some researchers have argued could be consistent with past or ongoing internal activity. A magnetosphere temporarily stripped of plasma by an external solar wind event looks, from a distance, identical to a magnetosphere that simply has nothing to detect because nothing is happening beneath the ice. Telling those two explanations apart requires exactly the kind of return visit the Decadal survey is now recommending, because no amount of reanalyzing 40-year-old data can substitute for actually being there when conditions are normal, with instruments running continuously across weeks or months instead of a single rushed pass measured in days. Uranus has been visited exactly once by exactly one spacecraft for less than a week in nearly half a century of space exploration. Every paper written about its magnetosphere, every model built to explain its behavior, every assumption baked into subsequent research, all of it had no choice but to treat that one narrow window as representative, because there was no other data to compare it against. It took a solar physicist looking specifically at upstream solar wind conditions, using methods and instruments modeling techniques that did not exist in 1986, to realize the original snapshot might have captured the planet at its least typical moment rather than a fair baseline. Linda Spilker, a NASA planetary scientist who worked on the original Voyager mission and was not involved in the 2024 reanalysis, described the original flyby data as exactly what it was always going to be: a single snapshot in time, not a complete picture. None of this would have been possible without Voyager 2 specifically, and it is worth being precise about why. Voyager 1, for all its own historic achievements, crossing the heliopause first, becoming the first human-made object to leave the solar system, sending back the pale blue dot photograph, never carried a magnetometer past Saturn's moon Titan. It has no Uranus data to reanalyze, because it has no Uranus data at all. Every insight now emerging from this 2024 re-examination exists only because Voyager 2 happened to be sent on the trajectory that let it complete the full grand tour of the outer planets, an opportunity created by a planetary alignment that will not occur again until the 22nd century. If NASA had sent both spacecraft toward Titan, or if engineers had made a different trade-off back in 1977, humanity might still have no direct measurements of Uranus's magnetic environment at all, compressed, distorted, or otherwise. Voyager 2's unique trajectory has paid off in one more way that has nothing to do with the outer planets themselves, and everything to do with what lies beyond them entirely. In November of 2018, 6 years after Voyager 1 made history by crossing the heliopause and entering interstellar space, Voyager 2 crossed that same boundary from a completely different direction, becoming the second spacecraft ever to leave the protective bubble the Sun carves out of the surrounding galaxy. Because the two spacecraft exited the solar system at different angles, one heading up and out of the plane where the planets orbit, the other angling down and outward on a separate path, scientists suddenly had two independent vantage points on interstellar space instead of just one. When researchers using both spacecraft's plasma wave instruments later found that the density of material in the space immediately surrounding our solar system was rising, and rising in a way no existing model predicted, that finding held up specifically because it showed up independently in data from two probes approaching from two different directions. A single spacecraft finding an unexpected density gradient could plausibly have been dismissed as an instrument quirk. Two spacecraft, launched decades apart in trajectory planning, confirming the same unexpected trend from opposite sides of the solar system, is a great deal harder to wave away as noise or coincidence. That confirmation, published in the Astrophysical Journal Letters, simply would not exist without Voyager 2's presence on the far side of the boundary, doing something Voyager 1, alone, could never have proven on its own. The renewed attention this discovery has brought to Uranus is already shaping what comes next. The most recent planetary science and astrobiology. Decadal Survey, the document that guides NASA's major mission priorities for the coming decade, identified a dedicated Uranus orbiter and atmospheric probe as one of its top recommended flagship missions, a project that would finally give scientists more than 5 days of data to work with. Such a mission, if funded and built, would not launch for years and would not arrive at Uranus for a decade or more after that, meaning the planet may go on being understood primarily through a single, now partially discredited flyby for a long time yet. In the meantime, the 2024 reanalysis stands as a quiet but significant example of how much remaining discovery is still buried inside data that is already decades old, sitting in archives, waiting for the right question, the right method, or the right person to look at it again. That is, in the end, the real story hiding inside a headline about a compressed magnetic field. Voyager 2 did not need to fly anywhere. New in 2024 to rewrite what we know about Uranus. It had already done the flying in 1986 using instruments and computers that were primitive, even by the standards of their own decade. The rewriting happened decades later on Earth, when scientists finally had the tools and the patience to ask whether the single window humanity had ever gotten was actually representative of anything at all. Voyager 1 crossed a boundary no spacecraft had ever crossed before and kept going into the dark beyond our solar system, a genuinely singular achievement that nothing built since has matched. Voyager 2 did something different, and in some ways just as remarkable. It looked closely at 4 worlds no other spacecraft has visited since, and left behind a dataset so rich that scientists are still finding new discoveries hidden inside it. 38 years after the machine that gathered it moved on and never looked back. Somewhere in that gap between the 2 spacecraft's legacies is a useful reminder about how science actually accumulates. It is rarely a single dramatic moment of discovery, followed by settled certainty. More often, it looks exactly like this. A 5-day flyby in 1986, filed away as fact for nearly 40 years, until a researcher with a new question and a better model went back into the archive and found that the fact had never been quite as solid as everyone assumed. Uranus has not changed in the time since. Voyager 2 flew past it. What changed is our willingness to ask whether we ever really understood it in the first place, and the only reason that question could even be asked is that one spacecraft, on one unrepeatable trajectory, happened to be there to take the measurement at all decades before anyone knew there would be a reason to look back.